हाँ इसका माइक ऑन ठीक हो नहीं है we are already recording. No. This is recording. So stop it.
A little bit about some portions of this because what I'm going to talk about has been somewhat in the news recently. But in my sort of big thesis is sort of obvious to some extent is that we as a nation are net consumers of the entire computing stack. And I'll talk about what the computing stack means in the context of desktop. And what we have to sort of move towards is towards being net producers and net consumers. I teach a language, I teach a course of programming language design. And this is what I sort of talk about as being the objective of that course is essentially students when they come to that class are net consumers of programming languages. They know how to write programs in various programming languages, but the goal of a programming languages design course should be to make them aware of how they can become net producers, how they can sort of learn about what it takes to produce a new programming language, possibly from right? I'm not going to say that it's an easy problem, it's a tough problem, but I think it's worth solving for multiple reasons, that some of which are enumerated in this. Right? So again, I want to talk about this concept called sovereign compute. Right? It's sort of made up of two parts, sovereign and compute, and I'll pick them up one by one. Right? So let's go with sovereign first. If you go to Cambridge Dictionary online and look up what sovereign means, it is essentially, it says having the highest power or being completely. I'm going to focus on this being completely independent part of it to some extent. So when I talk about compute in the context of this talk, I will talk about what would it take for us to become to some extent independent. I think in this interconnected world of today, you can't be completely independent in any aspect whatsoever. But you can strive towards reducing your dependence on other people, especially in the context of compute in this. Right? So again, this is what I'll sort of work towards as sovereign or as a meaning of sovereign, which is being somewhat independent, but not completely dependent on outside entities as far as compute is. Right? Okay, so that's one. Now, coming to the second part of this thing, which is the compute part. Right? So, when we think about compute or just the word itself, in 2024, these are the things that come to mind. You have your mobile phones, you have your laptops, you have your tablets, and then multiple other things. Almost everything that we see around us these days has some form of compute built into it, whether they be wearables, whether it be your Alexa, whether it be your Roomba that cleans the floors, whether it be your electric or regular car. Right? I mean, even regular cars today have a lot of quote-unquote compute built into the form of microcontrollers. Right? To the extent that recently I saw a tweet where somebody was using an LG washing machine, which was sort of listening in on the surroundings. It was apparently a smart washing machine connected to the internet and consuming 3.5 plus gigabytes of data every day. Right? So there's some compute built to that washing machine itself. God knows what for, but it's there and it's consuming 3.5 gigs of data every day. There are various ways in which we interact with quote unquote again compute pieces. On your phones, you have multiple apps. On the non-mobile devices, whether it be your desktops, whether it be your laptops, you interact with compute that is either executed locally. So you have your Microsoft Word, your browsers, whatever else you have on the laptop itself. And then you have other applications that kind of talk to compute that resides elsewhere. Right? So for example, your Gmail, your YouTube, you're consuming content on your laptop or your mobile device, but the actual processing of it, the retrieval of information is happening on compute that is located far, far away in things that look like these, right? So these are sort of like the data center racks of 2024, and a lot of things that we do today, ordering food on Swiggy, ordering stuff on Amazon, digital transactions, online banking, everything that you do today on your mobile phone or a laptop, at the end of the day is powered by a bunch of servers that sit somewhere in a data center and look like this, right? So when we sort of talk about quote unquote compute, these are the various things that kind of power our everyday devices, right? But the connotation of compute or what actually compute means, or if I have to point to something and say, okay, show me a device that computes, if you go and ask most computer scientists or computer engineers, they will point you to things that look like this that do your actual compute, right? They do your additions and multiplications, whatever happens. Right? In the most traditional sense, you have your CPUs. And these days, because of AI, LLMs, everything else, non-traditional compute like GPUs, wafer scale engines, CPUs, this is the tensor processing unit from all of these things have also become relatively common. And if I go back to this slide over here, in these server racks, the compute, the backend compute of all the devices that consume, all the applications that consume from the laptops or the mobile devices, is powered up not just by traditional compute, which is your CPUs, but more and more so by non-traditional computers, your GPUs. So for example, if you are consuming applications that um, access an LLM inference endpoint, that might be running somewhere over here on a GPU, somewhere over here on a TPU, so on and so forth. So, but when we think about compute, these are the things that typically people would point to, right? So when technologists talk about, oh, let's go develop compute, what they really mean is let's go develop a novel CPU architecture or GPU architecture or some non-traditional compute that has been designed specifically for accelerating a group of tasks, right? And but the problem is this compute by itself. So if I design a CPU or a machine learning accelerator or a normal GPU or something of that sort, it really can't do much by itself. Why? Because most machines today are one-on-one machines, right? So you need a CPU or some compute unit that actually does the calculations and makes certification calculations. But you also need other peripheral components around it, like the memory where instructions and data is actually stored, which has been brought in here. And by and large, we have not been able to move away from this. Right? So any compute device, any sort of server rack that you can point to today, essentially follows some version of this one human, right? Which essentially means to create a fully blown computer system today. Not only you need to have those actual compute units, so CPUs, GPUs, and GPUs, but you also need to have a bunch of other things available within the ecosystem. What are these other things? You need to have actual memory, right? So this is our DRAM DIMM. right? So this is just the hardware aspect. Right? So if I want to assemble a server machine today, I'd have to go find a motherboard, I'd have to go find each one of these components in addition to the type of compute unit that I want to do, put them all together, power this up, and then maybe I can just boot this machine. Right? So that's stage zero. I have put everything together and I have booted this machine up in order to sort of get get a computer, quote unquote, right? But the computer by itself is actually worthless. Right? I mean, I can't really do anything. In order to be able to utilize that computer, I need to be able to write programs against that, right? And in order to be able to write programs, I need an entire ecosystem to be present. So what I've been talking about so far is just the entire stack, which is just the hardware part. Okay? I have assembled a server and I've been able to boot it up. But in order to make it usable, I need to have a bunch of other stuff as a part of the ecosystem up and running before I can do even the first useful thing that we do. I need to have system software, which essentially is you have to have your operating systems, you have to have your compilers, you have to have your linkers, loaders, whatsoever, which is capable of running on the hardware that you have designed. Right? And that's one of the reasons why designing new chips is relatively challenging, is because if you design against a non-traditional ISA, then you have to code this entire layer on top, which is system software, operating systems, compilers, so on and so forth, for this new instruction set that you use. But anyways, so I have to have this. Then having an OS by itself can't do much for me, right? Because all it does is gives me something that can manage all the resources that I have put together as a part of this server system. Right? So, okay, fine, I have put the software, but now I need my languages. There is a language that I'm comfortable writing programs in. These days, it's not going to be C, it's probably going to be Python, Java, some more managed language that people are. So I need to code that. Once I have this entire stack ready, right? So I have hardware, I have the system software that is ported and works against this hardware. I have ported languages and runtimes to work against this hardware through the system software. Only then I can actually start writing applications against this stack and make this useful, right? So when people, so the point that I'm trying to make here is that in order to be able to utilize hardware, novel or otherwise, you have to have an entire ecosystem in place, which is non-trivial to set up, especially if you are trying to develop new architecture, for example, right? Usable. And once you, and you know, assuming that you have gotten the part where you have designed your hardware, the system software lifecycle eventually has to kick in, where you have to have maintenance for your operating system, your compilers, things break, right? So they need fixing. There are people who would need to do that, right? All of these things we need to have before we can, like I said, start utilizing our hardware. Now, we are very much used to utilizing this entire compute stack as we know. I mean, I get applications on my laptop, I run applications in the cloud, so on and so forth, using some hardware, some operating system, some programming language, some combination of linker loader, whatever. Now the question is, what fraction of these things that you and I are writing our applications against today, which fit in any one of these four boxes, are things that have been developed in India? Right? Consider a hypothetical scenario where we go to war with everybody else on the planet, right? In that case, geopolitical tensions are on the rise, and everybody says, well, I'm not going to make use our technology until all of this is kind of sorted out. And all of a sudden, I have access to nothing, right? I can't access the cloud because that is somebody else's. Somebody else pulled my license to use OpenAI because again, that's not our LLM. We have nothing else that we have developed in-house that we can migrate to overnight. And also that is something, I mean, even if we have something that has been built, that does not necessarily mean that it's usable, right? So there's one thing that is building indigenously, and there's something else which is building indigenously and making sure that it's actually usable and has a decent enough user base and is sort of quote unquote known enough that people will start using it, right? So, anyways, out of these four boxes that make up the entire compute stack today, all the things that we produce in-house in India, develop indigenously, is actually zero. We don't do any of this in India. And let me sort of talk a little bit about what the problems are with importing everything. Right? So first is if you talk about just the pure economics of it, right? Hardware in India is X% costlier than an equivalent hardware somewhere in the West because everything is quote unquote imported, so you have to pay import duty, right? So whatever could have been probably a laptop worth 90,000 is now a lakh and a half because I pay a lot more import duties on it than somebody else who's sitting in Singapore or in the US, right? So it increases the cost for me, the end consumer, which is again sort of a bad thing. If all of this was sort of manufactured, hypothetically manufactured in the country, the duties would not be high or as high, and I would get this exact same laptop or something similar for way cheap. Right? So from a very, very economic angle, it makes sense to sort of make things local. Correct? Supply chain disruptions. All the DRAM, all the CPUs that go into your laptops or your mobile devices or whatever else come from outside, right? So we are dependent on a few fabrication plants across the world to give us our SSDs, to give us our DRAMs, to give us our CPUs, which essentially makes us grow to supply chain. Right? If an earthquake happens in Taiwan, where the SMC's major factories are located, and they get shut down for a month, right? That all of a sudden will disrupt the supply chain of mobile phones in India, right? Because you can't get DRAM, you can't get CPU, you can't get something else. All the prices of those things might go up. None of those are good things, right? And this has actually happened, right? So there have been a couple of instances where some factories who were producing components like DRAM got shut down because of various things, earthquakes and stuff like that. And that raised the prices of DRAM, which in turn raised the costs of the devices worldwide. This was a while back. But again, the idea is that these kind of things can happen. And if you're completely dependent on supply chain of all of these components coming from outside, then you really have no control. I mean, if things go down over there, then you are just sitting here twiddling your thumbs, waiting for things to get sorted out there. Geopolitical relations, right? So again, I was talking about the example of OpenAI. Right? I mean, a lot of people are writing applications against OpenAI, and this is all fine and dandy so far, because we right now have a good relationship with the United States. If tomorrow that changes and United States decides to put us on the restricted technology use list or something that they come up with, then all of a sudden all these startups that have started writing applications or OpenAI wrappers go for a toss. They just start to shut down. And again, I mean, this is not an exact analogy in hardware, but it sort of gives you an idea as to what can potentially happen if you don't have indigenous capabilities at all. Right? There are a lot of possibilities of supply chain attacks, and that has increased in in the recent past. So, if your entire supply of all the components comes from outside, then there is a possibility that actors who are not, people can sort of insert themselves into their into the supply chain of either the software or the hardware and infect those devices or the software so as to be able to collect information on, right? So you could potentially have little Trojan horses that are sitting in your compute devices that are coming from outside because you really have no control over where those things are being manufactured, right? Similarly for software, closed source software, especially that is coming from outside. So if you're just importing things, and that has implications for security of not just data, but also national security to some extent as well. Again, the more things you manufacture within the country, the more jobs you are going to have. Factories are being set up. People are designing CPUs. People are designing memory systems. There is a complete set of industries that come up around these four areas because then you have suppliers who will supply components that these manufacturing units that come up are actually going to be. Right? So, and again, like I said, it's always better to be a net producer than a net consumer. Right? Okay, so I'm going to sort of move a little towards talking about what have you tried so far. Now I'm going to talk a little bit about both the hardware aspect of it and the software aspect of it. And it's not going to be a very long list because frankly we haven't done much. Right. So as far as the actual compute manufacturing goes to some extent, we have this thing called the Semiconductor laboratory in Chandigarh. So it's the only one unit in India that can actually sort of do fabrication. But then again, it is quite an old technology. But that's okay. I mean, at least there is some capability. It's 180 nanometers right now, we are at 2 nanometers. Right? So it's quite old. But then again, the good thing is it's there because not everything that you manufacture needs cutting edge technology. I mean, it's nice to have that, but you don't necessarily. You can do a lot with 180 nanometers as well if you have it. Right? So at least we have that before. Now, what exactly is that doing in whether it's manufacturing things at scale? I don't know, but I know that it's there, so we have some capability there. There's something called the National Supercomputer. I don't know if anybody heard of that. So that's my favorite whipping horse, actually, when it comes to pointing out how things that have started with good intentions actually went wrong. Right, so the National Supercomputing Mission was something that was started with the intent of developing indigenous capability in being able to design hardware, right? Supercomputing hardware. Within there, it was supposed to be done in 3 phases. It was a large project, 4,500 crores actually allocated to it. It was supposed to be done in 3 phases. The first one was capacity building. The second one was installation. The third one was developing the capability to be able to design things indigenously, at least if not manufactured. 4,500 crores actually doesn't get you very far. What ended up happening is, out of the 4,500 crores, one of the questions the parliament was asked, and we have only ended up spending 1,218 crores, which is not chump change, but the real question is, where was that money actually spent? Right? I mean, was that spent on developing capability or capacity, right? And most of that 1,218.14 crores was spent on developing capacity. So you've heard of a lot of supercomputers and a lot of IITs being inaugurated, which would be installed as a part of the National Supercomputing Mission. Then there was some amount of training that CDAC did for people to be able to use those supercomputers. But that was pretty much the extent of it. We really did not develop any capabilities as a part of this mission. And as far as I'm concerned, this was a complete failure. Right? Okay, so at least the good thing is we've been trying stuff, right? So at least from an experimentation perspective, I'm kind of happy that people keep coming up with these things to be able to, you know, try. There's another project that's, I think, still active at IIT Madras called the Shakti project. And this was one of the 2 or 3 projects that has been somewhat successful to some extent. Successful because one, they sort of were able to tape out a few chips, test them, boot Linux on top of them, so on and so forth. And actually, they also spun out a company from this project called Info, which is, I think, based in IT Madras's incubation part. But the good thing is, they you can have a lot of questions about what's a novel about. There's nothing novel about it. It's the capability that they have developed. It's a lot of work designing a chip, fabricating it, testing it, getting it to a point where you can actually boot a full-blown operating system on top of it. And that is a non-trivial capability to have within the nation, right? So even if people come and say, oh, what's now Shakti? What they are sort of, the point is that I'm actually missing is that it builds the capability where we can actually do this today, right? The other good thing was it has sort of built an open standard. So there's an instruction set architecture called RISC-V, which is completely free. So if you design a chip against that instruction set, you don't have to pay a royalty to anybody, right? As opposed to ARM. So that's good, right? I mean, there is some capability in the country where we can actually sort of do this, right? There was something being done at IIT Bombay a while ago as well. You might know. There was actually, I think it was 2018, 2019, based on the Spark ISA. It was out there, it was manufactured, I think it was tested as well, but did it go anywhere? I don't know. CDAC keeps coming up with a bunch of ideas. So they had something called the O microprocessor with 96 cores, which was based on the R instruction set, I think. Again, what happened to that? I don't know. I couldn't really find much information on that. There was a roadmap on this website or one of the CDAC's website, which did not have on the x-axis, which did not have time. Right? So there was a roadmap without time limits, which is I don't know what to make. But anyway, the good thing, like I mean, focusing on the positives rather than nitpicking is actually we've been trying things. There is something else that CDAC tried as well, which is again sort of like a sister project to Shakti in the sense that there's one called the Vega processor series, is also based on the RISC-V ISA supported by MIT to some extent. They have manufactured and designed a few things, but then again, they have, I think, an SDK available. They have some boards available against which you can write software. So it has gone further than a lot of the things have gone before. But then again, how widespread is the use of this thing exactly? I'm not entirely sure. Again, focusing on the positives, some things being done. So there is some capability at 2 or 3 places within the nation where we can say that design from scratch, built, manufactured, tested, booted up. Right? The recent government has started this new scheme on production linked initiative. So the goal here is to entice foreign players by giving them incentives, tax breaks, whatever, so that they set up manufacturing capability in India. So there is one that's coming in SAM, built for 27,000 crores, built in collaboration with Tata. Not entirely sure what exactly is it going to be, but at least something's coming up. There's something coming up in Gujarat, Sanand as well, which is a micro factory that should manufacture something. And again, I don't have a lot of information about what exactly is being done there, but then again, there is some capability being developed there. And you can always make the case for that Micron is not Indian, but at least there is some benefit to having an ecosystem being set up, even if it is at the expense of taxpayer money because, like I said, it develops capability, right? I mean, the client's going to come in, it's going to require people to work there with a certain sort of technical expertise. Those will have to be trained here. Um, over time, more and more people will go and work there and develop an ecosystem with which better things can happen hopefully into the future. Right. So again, there are always pros and cons of giving large tax breaks to foreign companies, but again, overall, I'd say it's a good thing. Right. So that's sort of like the hardware and gateway. Right. So when it comes to compute CPUs, you have actually some capability. The rest of the hardware ecosystem that I talked about, network devices, SSDs, memory, etc., nothing that I'm personally aware of, and I could be wrong. But we don't have any capability that I'm aware of in those niche areas. Now, moving up the stack a little bit, operating systems, programming languages, runtimes, zilch, right? I mean, we really have nothing. If you do a quick Google search, you'll come up with these three things. So Julia has a Bangalore connection because apparently Viral Shah was in Bangalore when he was starting Julia, but that's pretty much the extent. Visual J Plus was or J Sharp, so it was developed at software C, and there are a few sort of toy languages that people have developed over time, but nothing serious. GCC Resource Center at IIT Bombay was a great thing that happens to a compiler ecosystem, at least for a long time. It trained a lot of people in GCC internals. Some amount of indigenous expertise was created because of the training, because of the courses that the GCC Resource Center at IIT Bombay did. But again, I think that is not active in as far as. But OS language runtimes, we really have nothing. I sort of dabble in architecture, and I can count the people who work in architecture research on two hands. I can count the people who work in operating system and programming languages in India in one hand. Right? So that's the kind of expertise that we have now. But the good thing is, I mean, there's only one way to go from here, which is up. Right? So you can't really get any worse than that. Okay, so having sort of whipped the horse quite a bit. Now let's talk a little bit about what this sovereign compute notion is for the group. Okay? So, like I said, compute or just the hardware component of it by itself is actually not not easy to do, but by itself it can't do much, right? Until unless the entire ecosystem around it is put into place to make the hardware usable. And then the idea is that we should own and operate some portions of the entire stack. Right? And in terms of actual compute, we have some capability, but as far as everything else up the stack, and most of the things within the lowest layer of the stack, which is hardware, we really don't have a lot of expertise. Again, out in the open, private companies might have that, but not a whole lot of expertise within, let's say, academy. So why hasn't bunch of these things that people have tried over time, or most of it, the government, why hasn't it worked so far? So again, there was not a whole bunch of, there was not a large market until very recently, right? So the purchasing power parity or purchasing power was low. Not everybody was able to afford computing devices, so it didn't make a lot of sense to invest in something which is sort of extremely capital intensive, not just the design aspect of it, but also the fabrication aspect of it, and especially the kind of money that is required to build fabrication plants is extremely hard to do. Governments can do that, or extremely high net worth individuals, or large companies like Intel or AMD can do that, but a startup can't set up a fabrication. Right? We've not been able to do sort of hardware very well, as opposed to application software, which we have done extremely well, because again, research, development, test iterations for hardware are very, very long. Right? That's one. And even to get started, the barrier to entry is very high because the tools that are required for you to sort of start hardware design are quite expensive. Right? So again, because there was no indigenous market and a bunch of other things, there was not a whole bunch of, or not a push for developing this capability in-house by multiple sector governments. The only sort of government entity that I know of that has dabbled in doing something like this is CETA, but also that has not gone very far, right? And this is again one point that I keep making is in Indian university, we don't have a critical mass of computer systems faculty. We haven't, I mean, in order to be able to sort of build capacity, you need to have that critical mass of people. If you have 100 people who are working in these areas, then maybe 20 of them will get together and take up a big project, or maybe even five will get together and take up a big project, right? But if you have five people working in this entire area, then it's very hard for them to be able to take up big, challenging, long-term projects to build things, build capability, build capacity, all of those. Because I mean, everybody else has a lot of things on the plate to begin. Right? So, okay, I have a 5 minutes. So, what all can we do? Right? So, again, I believe everything eventually boils down to. So, okay, tools are hard to build, tools are expensive, capabilities hard to build. That's all true. But then eventually it's the people who are going to do things. So then we have to sort of develop the capacity of people to some extent, right? And again, it's a very chicken and egg problem, right? I mean, if you don't have a large number of people who are capable of training a even larger number of people, then that critical mass of faculty, for example, or experience, etc., becomes the problem. Again, much more government funding for building the ecosystem, and once that is done, and there are a few good products that have been built indigenously, giving them a preference in procurement, especially for let's say government. Government is trying to do something of that sort, but very haphazardly, right? Again, like I said, there has to be bigger push on building culture in universities, which sort of lack to some extent. Develop open source tooling. You know, like I said, developing hardware has a larger barrier to entry because these are expensive. So if we can develop the capability, and like I said, right, I mean, develop this, develop that. It's the people who are going to develop all of these things. So eventually all of this boils down to sort of creating a cadre of students, enthusiasts, researchers, faculty, students who are enthusiastic about actually building. We don't seem to have that culture quite. One good thing that Shakti and they have done is they have built an open stack. Right? So that gives them a lot of flexibility to be able to do things without having to worry about eventual costs down the line when they start manufacturing things at scale. Right? So sticking to open standards is actually a good thing. And not just an open standard, but also something that has a user base to some extent. Right? I mean, I could choose some niche ISA which is freely available, but it has no users. There's no point building hardware for it. Right? Because, like I said, all of the other parts of the ecosystem, the operating system, the languages, and so on and so forth, will still have to be ported. Right? So having an open source instruction set in this case is useful because all of that ecosystem, somebody or the other, is actually working on porting that for this time. Right? Again, we have to try and build hardware again. All components, some part of it we have tried to build or at least push, made a push towards developing the capability, but we need to have actual fabrication capabilities in-house, right? So again, just to quickly summarize, one, we need to have some amount of sovereignty in compute, which is essentially to reduce our dependence at this point in time, complete dependence for everything on the compute stack that we use today on external entities. Except for applications that we write ourselves, probably. Everything else is kind of imported wholesale to some extent, right? So we need to own some parts of the supply chain. And you can always argue whether that's necessary or not, right? I mean, if Python is freely available, why bother creating a code? That's not the point, right? I mean, the point is that if you develop the capability to create another Python, if God forbid you have to create that Python tomorrow, you at least have that capability, right? But again, like I said, you have to develop some expertise and communities because eventually it boils down to people who are going to do this. I mean, it's money is good, push from the government is good, but it's eventually going to be a group of people who are going to come down and say, okay, we are going to sort of do this. We are going to make this chip here or design the DNA. Right? So this was kind of interesting. This report that or this news report that came in, I think, a couple of days ago, yesterday, where kind of India, I think, reported that India had less than 2,000 skilled engineers developing AI applications. I don't know what to make of that, but I thought that sort of fit into this larger thesis that I was going to talk about with you. So, seemed funny to sort of put it here. But anyways, that's all I have to say. Up to date questions.
One question.
Sure.
Did that much on this aspect? One thing is I don't know how the order restrictions apply to this, right? Assuming that it's not there.
I actually, that's good point. I really don't know how the licensing, various licenses actually work, and if that would be affected if some of the predictors have. But even there, we have.
So the example that's given is the so the open source package maintenance keep the scanned copies of the books because the software was not allowed to just scans, and then that was I guess restrictions could be worked around.
Right. That's a good point.
I have a question. So it's related to LLM. Like you mentioned, all compute is being imported from outside, right? So I'll share some background. Like, if you go back like 3 years, LLMs were not that popular and deep learning wasn't that mature. So the compute involved at the time was lower. Like they were using not that expensive algorithms to train models. And then in 2022, like industry wasn't super actively looking in AI research. And then later on, LLM got popular. Industry felt that they could really transform how things work. But there was a lot of groundwork needed to use it in the industry, like in production. So they started putting a lot of effort to achieve that, right? Like a lot of money from various major companies like Google, Amazon, Microsoft, and with these efforts from the industry, we didn't right? Not sure in which direction and how well, but it definitely moved. And I tried something as well, similar like in February. I tried to fine tune a model, but it was a big failure, I would say. The data which I fed it wasn't that clean, it was quite bad, and it resulted into like really failure, big failure. And it involved a lot of cost as well, like compute costs from me and as well as other people like whom I was working with. Now, like training LLM is quite expensive, right? And now there's this perspective that compute is being exported from outside. And as you know, like there's other concerns as well related to resources, natural resources and stuff. which are being affected because of training LLM and stuff. And I'm not sure if India has those resources as well. Like majorly research for LLMs is being conducted outside. So yeah, what's your perspective on this? Like, if there's some way by which you can change interfaces or something so that you can train align elements in a better way, so that it has overall load compute and we don't like, even though we rely on outside world to import compute, but it doesn't affect that much. So what's your perspective?
That's a good point, right? So, see, GPUs became popular because that was the only compute model that was available at the time that could reduce the amount of time it took to train models without you having to do much else, right? So, for example, you could just write your Python code and somebody else has optimized the Python runtime, somebody else has figured out a way to schedule those jobs across the GPUs in the course so that your overall time for training that model reduces drastically, right? And that's why there is this mad rush for GPUs right now because the stack has been optimized for GPUs. So if you want to, not to say that you can't train your model on the CPU, right? I mean, you can, but it's probably going to take you 4x, 5x, 10x the time that it will take you to train that model on the GPU itself, right? So to your point, one is there are a lot of people who are trying sort of non-traditional, for example, that Cerebras wafer level chip, right? They have designed an entire wafer that is supposed to run, that is supposed to be an accelerator for, not entirely sure just LLMs, but AI workloads in general, right? But then again, to be able to utilize or make the most out of that wafer level chip, you have to have that system software sort of ported on top, right? Now, to be able to let's say where you want, you have a complete farm that's available to you, but you can't lay your hand on GPUs even though you have a lot of money. Then the better approach, at least in my opinion, would be to take your PyTorch implementation that runs on your CPUs and optimize the hell out of that, so that you can reduce your training time from X to X by 2. Maybe it's not going to be as fast as doing it on the GPU, but it's still going to be faster than just running it naively on CPUs. This is assuming that it's not your hands on GPUs, right? So again, if you have a certain time of compute available, lying unused, right? Then it's probably easier to spend either time optimizing the stack so that your training time for this traditional compute goes down, or to find models that can be trained quickly on this CPU type compute. So rather than training very, very large models with billions, tens of billions of parameters, maybe you train smaller models to do specific set of things with a few hundred million or few single-digit million models that can actually be trained and run as inference endpoints on CPUs that you already have lying around without having to sort of wait either for GPUs or spend a ton of money. So that's sort of my take. Again, it's sort of non-trivial to optimize the stack without that answer.
Thank you, Professor, for such an informative talk. We have arranged refreshment at the EC Hub. Please help yourself to continue our conversation with Professor there. Thank you, everyone, for joining, and have a great evening.